All right, so this question says the coefficient of kinetic friction, that's a lot of words, is 0.3. So what that means is it's some measure of the roughness of the surface. So we have a 35 kilogram box, and the mu, which is the symbol for the coefficient of kinetic friction, is kind of like a cursive U, if you learn cursive, is 0.3. What horizontal force is required? And that sounds kind of passive voice. They're basically saying a person needs to push on it. So I'm going to call that the force of the person to move the crate at a steady speed. So constant speed means the forces are balanced. So the nooks and crannies are catching on this box and causing force of friction, and nobody's winning. I know this green vector is bigger than the red one, but nobody's winning. The forces are tied. Because if the person was winning, it'd be speeding up. If friction were winning, it'd be slowing down. Nobody's winning, which means as quickly as the person is giving the box energy, friction is taking it away. Okay, so I hate that the book doesn't say draw a force diagram, so let's practice that. Does the box have weight? Yes. It doesn't matter in this case because the motion is left and right, and all the demos we did with Batmobile and drop and shoot indicate that like horizontal and vertical don't affect each other. But we still need to draw and identify the fact that this box is being pulled towards the earth. Okay, so there's weight. Are there fans? No. Is it touching a surface? Yes. In this case, the normal and the weight are equal. They're just balancing each other out, making sure the box doesn't fall through the floor. Is there friction? Yes. Friction is always opposite the velocity. That's the new rule from the PlayPosit. Please, friction is related to velocity, but draw this far enough off to the side that you don't accidentally include it as one of your forces, because it is not a force. It just tells you the direction of friction. Okay, and there aren't any ropes, so there's no tension. Okay, so since they did mention speed, but they didn't give you a number, and there's no time, and there's no distance. So this is an old school problem, and it's a horizontal old school problem. And plus and minus, so we have the force of the person minus the force of friction equals the mass of the box, which is 35 times 0, because it's a steady speed. So this is basically, you can just start with sum of the forces equals 0, but I kind of wanted to show you where it came from. Okay, so the force of the person has to equal the force of friction. Okay, so it still seems a little bit like you can't do the problem, but the new thing is, in our miscellaneous column, it's optional, but I think it's super helpful. That's where you will calculate weight if it's an up and down problem. Sorry, we do need to calculate vertically. Forgot they haven't done this yet. The sum of the forces are also balanced vertically. So this is a vertical problem and a horizontal problem. Okay, the normal force is positive. The weight is negative. Nobody's winning. So the normal equals the weight, which is 35 times 9.8, which is 343 newtons. So the surface is flexed, is stressed or pushed by 343 newtons. And I hope that makes sense, that the more the surface is squished, the more the nooks and crannies interact with each other. So the bigger the normal, the bigger friction. So friction is going to be 0.3, which is a measure of how interactive the nooks and crannies are, times the normal force, which is 343. That's a 4. So friction is 103 newtons. So the force of the person has to equal the force of friction, which is 103 newtons. Okay, it's a little bit tricky. It's a little bit convoluted. I think it's an easier to understand problem when they say, you know, find friction, and the person isn't the same. And then, you know, you like they say the person's like 200 newtons and then you do the problem. So it's a little bit tricky, but steady speed just means the two forces are balanced. Okay, so that was good practice with everything except for the old school. So we had some miscellaneous action going on here. We had some horizontal action and some vertical action. All right, 47. You're going to see once you start to do these problems, they're going to be really, really, really similar to each other. So your box slides across the floor. How far will it go? That's a distance. That's going to be old school. Given that the coefficient of friction is 0.2 and the initial speed is 4. Okay, this one's tricky in that they don't give you the mass. And so this means the mass is going to cancel. If that really bothers you, you can just make up you know what, let's just do this problem with a mass. And you can see in the paper answers that there is no mass. So let's say it is a 3 kilogram box. Okay, let's practice our forces. Everything has weight. It's touching a surface. This is what I call a boring problem. Those two forces are balanced. And what seems a little weird, that's why I put this kind of problem in the play posit, is you have the force of friction because the box is running into the nooks and crannies, but there's no positive force. There's only a negative force, and people find that kind of hard to wrap their heads around. So I don't know if I said this is a play posit, but the analogy would be like we put somebody on rollerblades and we give them an initial speed and we send them down the 9th grade hallway towards Miss Black's office, and everybody lines up along the you know, everyone else, and they give you a high five. They're slowing you down. You don't have a forward, you had a forward push, right? So something gave this box a speed of 4 meters per second. But now all these people giving this person a high five is like the nooks and crannies just slowing it down. So there is no positive force. Okay, that is your force diagram. Please ask to talk about it in class if you want to, either individually or as a class. That's your force diagram. Hopefully that's feeling good. All right, and we know we're going to need to do old school because it's asking about a distance, but let's do our miscellaneous first. So in the miscellaneous, I like to calculate the weight. So 3 times 9.8 is, and I actually don't have that because I did it with mass. Okay, so the weight of the box is 29.4 newtons. Okay, then you almost always want to do the vertical first because friction depends on the normal, and the normal is vertical. So vertically, the forces are balanced because it's not moving up and down. So the force of the normal minus the weight equals 0 because there's no up and down acceleration. So the force of the normal is the force of the weight. And I know I'm mixing and matching my notation, but that means the normal force is 29.4 newtons. Okay, so we know this and we know that. Then I would suggest you also calculate friction in the miscellaneous, just because makes, you know, having the weight all ready to go makes your life easier. Having friction ready to go makes your life easier if it's possible, if they're not asking you to solve for mu. Okay, so mu is 0.2, and it doesn't have dimensions because normal's in newtons and friction needs to be in newtons. So friction is 0.2 times 29.4. So there is 5.88 newtons of friction. So we now know this is 5.88. That's not a minus sign, that's just a random mark. Okay, now we're going to do horizontal. Horizontally, the forces can't be balanced because you only have a single force. So there's no way a single force can add to 0 unless it doesn't exist. So horizontally, the sum of the forces equals MA. The reason those plus and minus signs are nice is, oops, that should have been a minus sign. Psych. You've got negative 5.88 newtons of nooks and crannies pushing you back, right? All your friends giving you a high five is pushing you to the left. The box had a mass of 3 kilograms, and what are we looking for? We're looking for the acceleration. So the acceleration is negative 1.96 meters per second squared. That is how quickly it is slowing down. Okay, so we've done almost every column. We did our miscellaneous, we did our vertical to find the normal, we did our horizontal to find the acceleration. Now, the last thing we need to do is our old school. So x naught is going to be 0. X final is what we're looking for, how far it's going to go. V naught is not 0, or it would not hit the nooks and crannies. What is V naught? It is 4. A is negative 1.96. We don't really care about the time. V final is 0 because we want to know how far it went. So it came to rest. We don't care about time. So I would suggest we are going to use don't know, don't care. Okay, it came to rest. It started with a speed of 4. Don't go on autopilot and use 1.96. Sorry, and use 9.8. X final is what we want, minus X naught, which is nothing, so there's just a little bit of X in there. Okay, so 0 equals 16 minus 3.92x. We care about x. So let's subtract 16 from both sides. And then divide by 3.92. Sorry, by negative 3.92. And that's good because then we get a positive value for x, which is good because we knew it was going to the right. So 1.6 divided by 3.92 is 0.408. Oops. I got 4.08 in my answer key. Did I? Yeah. Yeah, I divided wrong on my calculator just now. Okay, so x equals, it traveled 4.08 meters before coming to rest. That's a pretty big distance. That was small friction. Okay, so again, you should be to the point, and if you're not, keep practicing. You see that we used every single column. We used the vertical to get the normal force. We used miscellaneous to get weight and friction. We used horizontal to find the acceleration, and we used old school. Okay, so individually, again, I think the hardest one right now is probably the forces because that's the one you have the least practice with. Okay, we got 2 more, and I didn't give myself enough room, so hopefully you're following along. And you'll just draw this on your paper where you do have enough room. Okay, so okay, we have a 72 meter long skid mark, which nearly came to a stop before colliding. The coefficient of friction is 0.8. That's high. Estimate the initial speed of the car. Okay, so clearly speed and distance, that means old school, and friction means new school. And I'm sorry, I should have redone these problems with making up a mass. But let's just make up a mass for the car. So it's a car. So let's say it's 800 kilograms. All right, so this is what's going on. Ignore that other problem. We're just going to do this problem here. Stop. Okay, so what happens is the car has some speed V naught. And the reason they're giving you this story is that it is my understanding that there are times, like if somebody dies in a car accident or has a serious injury, they will measure the skid marks. And I hope it makes sense. The faster it's going, the longer it's going to take to stop. So by measuring the skid marks, the police or the lawyers, if you're suing somebody, can say, look, you know, we know what standard conditions are. We know how fast you were going, and it was clearly well over the speed limit. So that's why they gave you this problem. All right, so again, hopefully at some point you'll say, oh, the friction problems tend to be pretty similar. It has weight. It's touching the road. It's not accelerating up and down. So these two are equal. And the car has inertia, so it wants to keep going that way. And the road is going to exert a force on it. It's complicated, but it's really the rotors, the brakes, and the wheels, but whatever. We're just, hopefully this makes sense. We're going to pretend like it's the force of the road slowing it down. Okay, so let's do miscellaneous. And I said that was 800. So the car is pushing into the road with a force of 7840 newtons. It's actually attracted to the earth with that much force. And vertically, you have two forces, and nobody's winning because it's not accelerating up and down. So the normal force is the weight. Eventually, I'm going to say, like, this is a boring problem, and eventually when you do these enough, you will earn the right to say, you know what, I don't need to keep doing this over and over again. The normal and the weight are the same in number. So once I find the weight, I know what the normal is. That's not always true, but with boring problems, it is. Sorry, that's a really, these are the same numbers. Okay, so we did our vertical forces. We found the weight. Let's calculate the friction now that we know the normal. This is the most fun formula. And friction was 0.8 because you want a lot of friction to not skid out. So the force slowing that car down is 6,272 newtons. So again, I like to have these calculations over here so that keeps the other columns a little bit more organized. So now we're going to do horizontally. Horizontally, it is decelerating. It is not going at a constant speed. But the only force acting on this car is the nooks and crannies, and that's how hard they're pushing. Equals M, which is 800 times A. So the deceleration of the car is negative 7.84 meters per second squared. That is how quickly it is slowing down. And what we want to know is what we want to know what V naught is based on, because we measured the distance, or the police measured the distance, and we assumed it came to rest. I know they worded it kind of oddly where they're like almost came to rest. So we're doing an estimate. So we're saying, all right, let's pretend like you pretty much came to rest. We don't care what time it happened. So it pretty much came to rest. It had an initial speed. Oh, that's what we're looking for. We found the acceleration. Yeah. And then this delta x is the skid, it is the distance you measured, you know, or you can always say you started your measuring tape here. Sorry, I want to make that yellow because it's a measuring tape, and rolled it out. So this x naught is 0. Okay, so came to rest. This is what we're looking for. So I'm gonna, this is 0 equals V naught squared minus 15.68 x. Oh, sorry, we know x. X was 72 meters. You get V naught squared equals 1129. So the square root of that is 33.6. And again, that's like 70, 75 miles an hour. It's more like, to convert, it's like 2.25, something like that, I think. Yeah, 76 miles an hour. Okay, so maybe going over the speed limit. Yeah, I guess so. All right, so that was the initial speed. So breaking this down again, miscellaneous is weight and friction. Vertical, boring problem, the support force equals the weight. Horizontally, a little bit goofy because it's, to me, I think it's hard to say, what am I subtracting from? But remember, that's not taking away from, that's just direction. Friction is pushing the car to the left to slow it down. And then you have your old school. All right, I'm going to pause the video, get rid of this stuff so we can do the very last question. All right, the last question. A cyclist is going at a speed of 12, but enter the muddy stretch where they're saying effective coefficient of friction because it's not really the same as nooks and crannies. So they're just saying, hey, we're trying to mix the problems up, not give you boxes sliding over and over again, just pretend like coefficient of friction is 0.6. Will the cyclist emerge from the muddy stretch without having to pedal if the mud lasts for 11 meters? Okay, so this is kind of an open-ended question. If so, what will be the speed? Oops, sorry. So let us draw the force diagram one more time. I'm just going to pretend like the cyclist is a box. So you have the weight. You have the support force. Again, they did not give you the mass. So let's say the mass of the cyclist is 64 kilograms. They have a speed of 12. Again, you can see this is really the same problem over and over again. And friction is slowing the person down, or the cyclist down. All right, let's go to our miscellaneous and calculate the weight of the cyclist. 627.2 newtons. We have done the vertical. No, I'll do it again, and you can skip forward in case you haven't watched the videos. Okay, vertically, it is not accelerating up and down. So you have force of the normal minus force of the weight equals 0. Force of the normal minus 627.2 equals 0. So the normal force is 627.2 newtons. Okay. Once you know the normal force in the miscellaneous column, let's calculate friction. So 0.6 times 627.2 is 376.32. All right, so we've taken care of the up and down forces. We found out what friction is, but we haven't figured out what it's doing to the object. So horizontally, sum of the forces equals ma. There is only one force, and it is negative. Friction is pushing to the left, causing it to decelerate. So the acceleration is negative 5.88. Okay, and then this is the open-ended part. Again, what you know is distance, and we don't care about time. So what we're going to do is we're going to use don't know, don't care. We're going to say, I don't care what time they get through the mud, but I want to know what their speed is at the end of that. And if they don't make it, what you're going to get is the square root of a negative number, and that will tell you they didn't make it. Hopefully that makes sense to you. And I can talk about another option at the end if I remember. Okay, V naught was 12. And we found out that they were decelerating at 5.88. The mud was 11 meters long, so we just decided to start the measuring tape where they started, and the total distance is 11. So you get V squared equals 144 minus 129.36. So 14.64, or did I not take the square root? That seems too big. I'm just checking my work. 144. Yeah, so V squared is 14.64. So V is the square root of that. So I have some units wrong in the paper answer. So the cyclist is going 3.83 meters per second at the end of the mud flat. So they did make it through. Okay. The other thing you could do is, there's probably more than one way to do this. You could say, when will they come to rest, and calculate what X is. I didn't do that, but you could do that, and you could figure out what X is. And if X is bigger than 11, then they could have gone through more mud, slowing down at that rate. So that's another way to do it. There's more, because it was an open-ended question. But they did want to know if it did make it through, what was the speed. So I think that's why we chose that method. Okay, so lots of stuff going on, as you know, usual with physics. We learn one thing and another thing and another thing, and then when we put it all together, it can seem overwhelming, but it is just a bunch of all the things we learned mushed together, just like choreography. So again, we're going to keep practicing, but hopefully this is starting to make a little bit more sense every day. So thank you for listening.